Hi guys, in this video we are going to discuss the differences between salient pole and smooth cylindrical or non-salient pole synchronous rotors. You know already very well, this is a salient pole structure. See, these are the poles which are projecting outside like this. And this is a smooth cylindrical structure, or there is no any saliency because there is no any salient poles here, right? So coming to here, what are the differences between them? First of all, the salient pole, nothing but the poles are projecting outside. What is that? The poles are projecting outside. That's why these are called the projected poles or salient poles. See here. Here poles are projecting outside. Poles are projecting outside. But here there is no any projections. There is no any projections. Simply the smooth cylindrical type is there. But here out of 360 degrees, out of 360 degrees, how much? 120 degrees of rotor periphery. 120 degrees of rotor periphery used for poles formation. Okay, and remaining 240 degrees used for slots or simply is called winding, just for winding. This is about the main differences, constructional view differences between salient pole and cylindrical pole. Here the poles are projecting outside, but here out of total rotor periphery, the 120 degrees for poles formation, 120 degrees nothing but, for example, out of 360, here 30 degrees of rotor periphery, 30 degrees of rotor periphery, 30 degrees of rotor periphery, and 30 degrees of rotor periphery. 120 degrees for poles formation. And remaining 60 degrees, 60 degrees, 60 degrees, and here also 60 degrees, completely 240 degrees for slots or winding. This is what about the cylindrical and salient pole. And coming to here, another differences between these two. See here, see carefully. When we are observing these two salient pole and non-salient pole structures, here the minimum number of poles. Of course, I drawn the 4 number of poles, but practically the minimum number of poles in this one is the 6 poles. And the maximum number of poles we can use here around 120. Nothing but simply the number of poles used in salient pole type 6 to 120. But practically what we are using in the range of 10 to 20 poles in that range. But here in cylindrical structure, the minimum number of poles used 2 and the maximum number of poles used 4. We can use either 2 or 4 number of poles, but here minimum 6, maximum 120, but practically we are using 10 to 20 number of poles. For example, for 50 Hz supply, what is the speed of the rotor with this many of poles? For 120 poles, the speed is 50 rpm. For 6 poles, the speed is 1000 rpm. So the speed range of salient pole is 50 to 1000 rpm. But practically what we are using in the range of 300 to 600 rpm. Because for 20 poles 300, for 10 poles 600. When coming to here the synchronous speed range or simply the speed range around 1500 to 3000 rpm for 50 Hz supply. In terms of 50 Hz supply. So simply here more number of poles, less speed, less number of poles, more rotor speed. Other than that, comparatively, the diameter of the salient pole machines much greater than the axial length. Generally, in this machine, the diameter is much greater than the axial length. When coming to here, the axial length of the machine much greater than the rotor diameter. Much greater than the rotor diameter. Or simply, more diameter, less axial length. Less diameter, more axial length. Actually, it looks like this. For example, this is the length. But here, the length of the rotor axis is much greater. So here more diameter, less axial length. The diameter is equals to around 5 to 7 times of the axial length. Diameter is equals to 5 to 7 times of the axial length. When coming to here, the axial length is equals to 5 to 7 times of the diameter. Axial length is equals to 5 to 7 times of the axial length in that case, but here diameter is equals to 5 to 7 times of the axial length. After this, when the diameter is more, ultimately the speed of the machine reduces. When the diameter is less, ultimately the speed of the machine increases. So simply here, what about the salient pole? What about the salient pole? What we can conclude? Less or more? Tell me, sir, how many number of poles? More number of poles. More number of poles, more diameter, less axial length and less speed. When coming to here, what you can say? Less number of poles and less diameter, more axial length and less speed or more speed, sir? More speed. This is the differences between these two. And the power output generally directly proportional to d square into L. The power output is equals to d square into L. Nothing but in order to get the more power factor, we need to maintain better diameter in salient pole, but in order to get a better power output, we need to maintain better axial length. Here the diameter should be less, that's why we need to maintain better axial length. So this is the main differences. And then after, what is the remaining differences? Simply this is used for low speed applications. Low speed applications, nothing but, can you tell me the example for that? The salient pole generators are used in hydroelectric power plant. The hydroelectric power plant, whatever the turbines, whatever the generator we have, low speed applications, the hydroelectric power plant generator speed in the range of 300 to 600 rpm. When coming to here, what we can say? High speed applications. We know that. Can you tell me the example for this? We can use in thermal and nuclear power plant. Thermal and nuclear power plant, what we are using the cylindrical type or non-salient pole type. Generally, the salient pole alternators also called hydro alternators. Generally, the cylindrical pole alternators are also called turbo alternators. Yes or no, guys? So these are the main differences between these two. Still we have some more differences based on the q axis and d axis. Okay, let's see the differences. And can you tell me, sir, which is d axis, which is q axis here? Generally, the d axis nothing but the axis which flowing through the pole centers. See here, can you tell me, this is the d axis or q axis? This is d axis. And can you tell me what is this axis? The axis which flowing through the pole centers, this is also called d-axis. This is also called d-axis. And when coming to here, yes, so can you tell me what is this axis? This is called d-axis as well as, and this is called d-axis as well as. These are the d-axis, and where is my q-axis? Where is my q-axis? Which is in quadrature with the d-axis. Nothing but the phase shift between d-axis and q-axis is 90 degrees to each other. Yes, so nothing but this is my q-axis and this is my q-axis. Yes or no, guys? Are you okay? Are you okay? Are you satisfied with my what I written here? This is my q-axis. These two are my q-axis. These two are my q-axis. The angle between q and d-axis is 90 degrees. Is it correct or not? Yes, this is 100% correct. Yes, the angle between q-axis and d-axis is 90 degrees, sir. Sir, actually here it's showing 45 degrees. I am not discussing in terms of mechanical. I am discussing in terms of electrical. The angle between q-axis and d-axis is 90 degrees electrical. What is the formula? Theta electrical is equals to P by 2 times of or pair of poles times of theta mechanical. Theta electrical is equals to how many poles are there? 4 poles. 4 by 2 into theta mechanical. What you are feeling mechanically 45 degrees. So 4 by 2 nothing but 2. 2 times of the 45 degrees which is equals to 90 degrees. Yeah, ultimately this is 90 degrees. And here also 90 degrees. Now can you see here once? In both the case, in which the air gap length is uniform. For example, here stator will be there, and here also stator will be there like this. Stator will be there like this, in which the air gap length is uniform. Let's see, here, if this is a stator like this, if this is my stator, see here the air gap length is more, but here the air gap length is less. Here the air gap length is less. Yes or no, guys? So, in this case, the air gap length along the q-axis much greater than the air gap length along the d-axis. But when coming to here, the air gap length is uniform along the d-axis and q-axis. Yes or no, guys? So, here non-uniform air gap. Are you okay, guys? Non-uniform air gap. What you can write here? Uniform air gap will be there. And if the air gap length is non-uniform, the flux distribution also non-uniform. Non-uniform flux distribution. What is this? The flux distribution? Generally, the field winding will produce the flux, which the poles will give the flux to the armature. Here the flux distribution is more, here the flux distribution is less, but here the uniform flux distribution will be there. But here non-uniform flux distribution. Yes or no, guys? When the flux distribution is non-uniform, then EMF is non-sinusoidal. I am removing this, please. When the flux distribution is non-uniform, then simply EMF non-sinusoidal. Here the EMF is non-sinusoidal. Non-uniform air gap, non-uniform flux distribution, then EMF non-sinusoidal. Uniform air gap, uniform flux distribution, then EMF sinusoidal. In which of the following case EMF is sinusoidal? In non-salient pole. In smooth cylindrical machine, we can have a sinusoidal EMF without any modification. Yeah, okay, sir. Now, sir, I want sinusoidal EMF even in salient pole also. So, what I have to do? To get the sinusoidal EMF in our salient pole machine, we need to do some modifications here. Like the pole structure should be like this. We need to change the pole structure like this. This modification is called chamfering. What it is called? It is called chamfering. So, what you can write here? By chamfering of the poles. What, sir? By chamfering of the poles, we can get sinusoidal EMF in our salient pole machine also. But here, no need of chamfering. What is the use of chamfering here? No need. Simply no need of chamfering in our cylindrical machine. But we need chamfering in our salient pole synchronous machine. Then after. So finally I will ask you one question. Which machine is more stable in between these two? Yes, can you tell me? Which machine is more stable? Sir, actually this is a sinusoidal EMF, right? That's why this is more stable. No, sir. The stability directly proportional to air gap, what I given you in the just a few seconds back, right? So the stability directly proportional to air gap, in which the air gap length is maximum. Simply in our salient pole, the air gap length is maximum. That's why the salient pole machine more stable than the cylindrical machine comparatively. What, sir? The salient pole machines more stable because more air gap. Because of more air gap, the salient pole machines are more stable. These are less stable comparatively because of less air gap simply. Right? So, final question. In this salient pole rotor, which type of winding we are using? In this cylindrical rotor, which type of winding we are using? Of course, if it is a salient pole or cylindrical, the stator having the same winding, short pitch distributed winding. When coming to rotor, in this rotor, which type of winding we are using? In this rotor, which type of winding we are using? Here, 2 points. Generally, where the winding structure denotes like this, that is a concentrated winding. Where the winding structure denotes like this with dot notations like this, that is a distributed winding. First point. And the second point, generally where the speed is minimum, there we can use concentrated winding. Where the speed is maximum, there we have to use distributed winding. Otherwise, winding will be delocate from the slots. If the speed is more, the winding will be relocate or delocate from the slots, coming out from the slats. That's why. So simply in our salient pole machine, what we are using? Concentrated winding. But in cylindrical machine, what we are using? Distributed winding. Which type of winding is this? This is a distributed winding. So these are the differences between salient pole and cylindrical. Generally in transformer, there is no any speed. We can use concentrated winding. No need to distribute the winding. Like that. Just try to remember. So finally, give me a conclusion for this. The salient pole and non-salient pole. Salient pole are smooth cylindrical. Okay, here in salient pole, more number of poles, less speed, more diameter, less axial length. Here, less number of poles, more speed, less diameter, more axial length. Turbo alternators, is it? No. Hydro alternators and turbo alternators. Here we need chamfering, no need of chamfering. Here air gap length is more, stability more, air gap length less, stability less. Concentrated winding, distributed winding. And you know the theta electrical is equals to P by 2 times of theta mechanical. And you know the basics generally, how many number of poles are there, that many of axes will be there. If 4 number of poles is there, then 4 axes will be there. In that 2 are the Q axes and 2 are the D axes. Generally. Okay, so this is a basic concepts you know already, I think. Yes or no, guys? So this is the differences between salient pole and cylindrical pole synchronous rotors. Thank you, guys.